Thank you for the invitation and for the introduction, Nick, and also Mike and Chris and Geneva. And Chris, just to double check, you can actually hear me, is that correct? Excellent. Okay, great. I'm going to tell you today about work that I've been engaged in over the course of the last few years or so. And this work is out in print, and it's also ongoing to some degree. And it relates to the theory of cosmic inflation, and in particular, the question of whether inflation is finely tuned. Now, this question has been live for quite some time. I think within a decade or so after inflation was set down, people were concerned about these kinds of issues, and some numerical work had been done. This issue was revived again more recently. What I want to talk about today is what I think is a different way to approach this problem, a way that uses another way to think about cosmic inflation, namely using effective field theories of cosmic inflation. So I'll be using effective theories to describe the issue of, and to try to lay out a program for addressing the issue of how finely tuned cosmic inflation may be. Okay. So this issue, as I said, has been around for a while. There was work done soon after inflation was set down that looked at trying to address this question. And the question, I think, again, arose in a different light as a result of a recent dispute that arose in 2013, 14, and so on. You can see the papers there on the bottom there, Ijaz, Said, and Loeb arguing that inflation has grown increasingly implausible as a result of some recent work by the Planck collaboration. And this was responded to by Guth, Kaiser, Nomura, and then others in 2014 and 2017. So it is the case that inflation is in fact very popular amongst cosmologists, and there are various experiments afoot, as I just mentioned, such as the Planck collaboration, and also some ongoing experiments. And however, as I say, right, people have some concerns. And one of the kind of concerns that people have raised is what I'm going to focus on. So the particular concern that I am going to focus on is this question of how finely tuned inflation happens to be. And I will think of this as part, or this particular question as part of an initial conditions problem for inflation, which encompasses this kind of question together with other questions too. But I'll be focusing on one aspect of this question of whether inflation is finely tuned, and I'll hopefully make clear what kind of aspect I have in mind. So as I say, I'll provide some context for this question, and then I'll try to propose one way of addressing the question in what I think is a modern and more comprehensive way than exists in the literature. And as I say, this makes use of effective field theories in cosmology. So I'll be talking about some work that, so this is a technical paper written in collaboration with David Kaiser in 2018, and we're continuing to work on these kinds of issues. And there's another paper in studies that addresses some of the foundational philosophical questions that I think surrounds at least part of this work. So there are, as I said earlier, other issues with inflation, and folks have written about this. I want to highlight one particular piece of work that I think is interesting. There are a number of problems that these folks highlight in this paper here, and the initial conditions problem is one of them. So if you're interested in them, in these kinds of issues, feel free we can chat about them at some point, or one can certainly take a look at this paper. So today, I want to provide you with some background on inflation to set the scene, to make sure we're on the same page. And then I'll talk about some of these problems for inflation, in particular the ones that are relevant for the kinds of concerns that I wish to address, and in particular the initial conditions problem, what I call the permissiveness problem. And then I'll talk a little bit about the promise of effective field theories of inflation and addressing in particular the initial conditions problem. So I will give you a brief introduction to EFTs of inflation, and say a few words about how EFTs of inflation address the particular problems that I have in mind, or have the potential to address those particular problems. And then I'll present you with some work that I did. This is work done in collaboration with David Kaiser that leverages these EFTs of inflation to tackle the initial conditions problem. And then I'll point out some aspects of the road ahead that I think one needs to address to really flesh out this program in detail. So, okay, so just to make sure we're on the same page, some of you may know this, by the early 1970s, a standard Big Bang model of cosmology had been established that described the universe just after the Big Bang singularity, and it faced problems that were explanatory in nature, I think. They weren't questions of empirical adequacy. Namely, the model stated but didn't explain why certain aspects of the universe that we observe today were the way they were. So in particular, the flatness, the flatness of spatial slices, the uniformity of the cosmic microwave background radiation, and some other issues which I'll say a little bit about in a moment. And then in 1980/81, cosmic inflation was posited, and the main claim here is just that just after the Big Bang singularity, the observable universe underwent accelerating expansion, increasing the universe in size by a massive factor, e to the 60 or 10 to the 26. So this resolves the flatness problem and the uniformity problem in ways that you're perhaps familiar about. The one thing I wanted to mention is that it's also the case that inflation provides an explanation for the density perturbations that are thought to be responsible for these anisotropies in the CMB and also for structure formation. So as I say here, by the time inflation was over, there were small differences in density across space, and these differences account for the CMB infrastructure. One could also think of this, if you like, as a fine-tuning problem for the Big Bang model of cosmology, which inflation addresses. So inflation can be described in this way as providing a solution to fine-tuning problems with the Big Bang model of the 70s. How do you realize inflation? Well, I think the simplest way to do this is by introducing a single scalar field subject to a potential and the action that I have set down there. So here's a schematic example of a potential, assuming, for example, that the field is uniform across space for the sake of simplicity. The value of the field tells you, or the position of this ball tells you the value of the field over the entirety of, say, a three-dimensional slice, spatial slice. And then the potential tells you how it is that this value of the field changes with time. You can arrange things with the right kind of potential and the right kinds of conditions. You can arrange things to such that you end up getting this accelerated expansion that I described. So the salient features of this, and I'm going to pause on this for a moment because I'll be referring to this kind of model in a little bit, is that you have a field phi of t and x known as the inflaton field. There's a potential term which tells you how the field changes with time and space in principle. So there's a canonical form for kinetic degrees of freedom for the inflaton, namely this kind of term here. And then gravitational degrees of freedom are encoded by the Einstein-Hilbert action, and there's minimal coupling between the inflaton and gravitational degrees of freedom, namely there's no sort of phi times I term in the simplest kind of model. So this is what I'm going to refer to as a single scalar field models of inflation. And then the natural question that arises is inflation realized in such a way, finely tuned, namely does it require special initial conditions? Okay, so why would you worry about this question? So here are some motivations for this question. So if it's the case that inflation is finely tuned, this calls into question its status as a theory that provides a solution to fine-tuning problems of the standard Big Bang model. So these three problems that I mentioned, flatness, uniformity, and the density differences that you require. These kinds of problems are fine-tuning problems in the context of the standard model, the standard Big Bang model of cosmology. And if inflation is finely tuned itself, right, there's a question that arises now how good of a solution it might be. You could also ignore that entire dialectic, I think, and you could just worry about fine-tuning in a theory. one might be inclined to be suspicious of finely tuned theories, that if things have to be set to be just so, that there is some sort of issue here. One way to maybe pass this is to say that when you're unsure of the physics at higher energies, namely in the Planck regime, that it's useful to develop accounts at lower energies that are agnostic about the details of this higher energy theory. So this is, if you buy this line of argument, there is a sense in which you are endorsing a type of genericness, that it's useful to look for lower energy accounts that are generic in the space of physically possible states, into which some higher energy theory may flow. So as I say here, and perhaps it's been famously pointed out, you may or may not find these kinds of motivations convincing. Penrose in 1989, in a paper titled Difficulties with Inflationary Cosmology, says that it seems to me that the idea of trying to obtain a universe in the form that we know it by applying physics to a time symmetric physics to a generic unconstrained initial state is badly misconceived. Nonetheless, I will proceed. And we can come back to this. I will, what I will do is I will restrict attention to problems of initial conditions as they occur at the energy scales of interest. So namely the energy scales that are expressly targeted by this new line of work on effective field theories of inflation. And this corresponds to the final 60 or so E-folds of inflation, as thought that this kind of energy scale is significantly smaller than the Planck energy scale. So this is not a talk about treating questions that probe whether inflation is somehow sensitive to a higher energy theory, to higher energy UV completions. It's a question which targets initial conditions at the sort of energy scales at which you think the last 60 folds of inflation started. So there is a natural question that remains then, namely, what kind of conditions are you in fact interested in once you have specified the kind of times at which you're interested in these conditions? So the kinds of conditions you could imagine asking questions about are really of two classes, I would say. One is where you're concerned about initial conditions that are homogeneous and isotropic, so where they're the same at every point in space and then the same in all directions. And there's some work there that I've highlighted by Raman and Carroll that addresses this kind of question. Or you could try and look at conditions which are the negation of the conjunction of homogeneity and isotropy, namely spatially inhomogeneous and or anisotropic initial conditions. And this clearly is a larger challenge. There are many more ways in which things can possibly go wrong and spoil inflation. And there's been some recent numerical work that I've highlighted here by East and Clow and Marsh and so on. Some more, and there's a review article here by Brandenburger that summarizes some of this work. And the general consensus that exists in the community is that, and this is the consensus among studies that do in fact go ahead and invoke specific potentials via phi, is that large field models of inflation are more robust than small field models. So there are kinds of mechanisms which have been revealed by some of these numerical studies, which give an explanation for why this might be the case. You might think that that's intuitively clear as well. Anyway, so a large field model is one in which the excursion of the scalar field during inflation is super Planckian. Okay, so there's a point to be made about this, and this is kind of where the work that I've been doing enters into this debate, that this consensus that I'm describing invokes specific potentials. And it's well known that there are a plethora of such potentials. There is a permissiveness problem, as I've called it, for inflation, that there are lots of different potentials that are consistent with the observations that we have collected. And so this, I think, presents an opportunity for addressing the initial conditions problem. So let me say something about this permissiveness problem to set the scene a little bit. This, I think, is just a problem of underdetermination of model by data. And it's daunting, and it's maybe not surprising, since the energy scales that are involved are very inaccessible. So for the simplest SSF models of inflation, these single scalar field models of inflation, current observations are consistent with all sorts of, so I should say a number of distinct models. And there are no agreed upon theoretical clues about how to constrain these. One can generate other models as well by modifying various pieces in the action that I showed you. So you can change the matter content of the universe by adding multiple fields, or you can try and take the gravitational degrees of freedom and modify them by, say, an R² term, as famously set down by Starobinsky. This original model, which gives rise to an inflation, is one that remains supported by the data today. So one of the motivations for studying EFTs of inflation is, I think, as a response to the permissiveness problem. So EFTs of inflation, as in the way that I will describe the construction, describe an inflationary phase in a way that's common to this class of inflationary models. And as such, I think there's an opportunity here to ameliorate the permissiveness problem to some degree. And I'll come back to why that's the case. But in light of the fact that the idea is that in light of the fact that we have all these models, say single scalar field models, particular class, maybe we can write down, say, model independent ways of thinking about inflation, extract predictions from model independent ways of thinking about inflation. And if, say, those predictions are not borne out, then you can rule out an entire class of models. This is the kind of sense in which you might ameliorate the problem. I'll come back to this. So, okay, so to these EFTs of inflation that I have in mind, that people have described. So more generally, an EFT describes a physical system as an energy scale, and in particular in bottom-up type constructions, they remain open as to the nature of the physics at higher energy scales. And they have been used extensively over the past 45 years in high energy physics and in condensed matter physics. And so it's natural to think that you might be able to develop them for cosmology, and people have, in fact. These kinds of ways of thinking about theories sit somewhere in between, I think, fundamental theories and phenomenological models. And as I say, people are now leveraging these kinds of ideas in the context of cosmology. So this has happened in the last 13 or 14 years or so. There's two foundational papers, one by Weinberg and one by Chung et al. In 2008, and they look to try and probe a general characterization of inflation around a preferred energy scale using bottom-up EFT approaches, a scale which is significantly lower than the Planck energy density. And the added feature, it turns out, by this sort of bottom-up construction, is that you get model-independent characterizations of inflation around this energy scale. And as I say, this provides a novel viewpoint on the initial conditions problem. Okay, so here's how it works. So I'm going to tell you about the construction, and I'm going to tell you how it is that we extracted information from this particular construction to probe the initial conditions problem. So in thinking about EFTs from a bottom-up point of view, you need three ingredients. You need physical fields that are thought to be relevant at the energy scales of interest, symmetries that underlie the theory, and then one constructs an action for the theory using these physical fields that are subject to the assumed symmetries. So I'm going to describe this particular approach by Chung et al. The physical fields that they have in mind is that the universe is described by some sort of a clock that simply counts down time until the end of inflation. So there is some sort of mechanism in the background that is functioning as a clock that is in fact breaking one of the symmetries of space-time and general relativity. It's breaking time translation invariance. So the other three symmetries remain. The other three symmetries of space-time remain. You're left with three-dimensional spatial diffeomorphisms. So the physical field is abstractly characterized as some sort of a clock. The symmetries you're left with are time-dependent spatial diffeomorphisms, and the action that you construct then relates to the kinds of degrees of freedom that you're left with. And in some sort of a 3+1 decomposition in the right gauge, you're left with just metric degrees of freedom. So you have the metric, so in a 3+1 decomposition, you have the metric, you have the extrinsic curvature tensor, and the Riemann tensor. And you have things like covariant derivatives, and then you have anything that is invariant under time-dependent spatial diffeomorphisms. So, so if you then take that kind of action, which I have not shown you, and specialize it in the case where you expand about the kind of background that is useful for describing observations today, which was the the original motivation for this, one of the motivations for this, you end up with this particular action. So this is an action that arises as a result of taking the clock, the symmetries, and expanding the resulting general bottom-up prescription about a spatially flat FLRW metric. You have two terms. One relates to the geometry, right? This R term arises, together with another term. This other term is really the clock degrees of freedom, right? And then you have a bunch of other stuff. This delta S contains general perturbations in the geometry and higher energy effects. So you have two kinds of expansions going on. There's an expansion in perturbations, and there's an expansion in derivatives, essentially, the usual kind of expansion derivatives that you get in effective field theories, together with this perturbation expansion. As a result of the fact that one of the issues that people are worrying about here is trying to describe phenomenologically the kinds of things that we see. Okay, so this should look somewhat familiar. I mean, this G00 is quite striking. So this is in fact right invariant under the symmetries. And in fact, anything with a zero index, upper zero index with everything else contracted is invariant. And so such a term will arise. So just to connect it to what we know, here is what this looks like in a particular context. Here's what this action looks like in a particular context. So if you're really interested in the dynamics of the background space-time, which is what we were interested in thinking about dynamical flows into inflationary states for a very specific aspect of the initial conditions problem, you can derive the field equations from this particular action. You can ignore the delta S term, which contains all the perturbations, and you can just focus on the background term. So so here's the action. The Einstein field equations are easily derived. H of t corresponds to the Hubble expansion rate, as usual. And you can compare this with single scalar field models of inflation. Single scalar field models of inflation are, in fact, a subset of the possible models that are covered by this kind of action. So here is that original action that I showed you. If you expand this action, if you write down this action in unitary gauge, so this gauge in which fluctuations in the clock degree freedom to first order vanish, so you effectively have a background which is homogeneous, then phi is just a function of time. If I put this into this particular equation, into this particular action, then I get two pieces here, one here in orange and one in blue or green. And you can see that there's a correspondence, right? I can make the single scalar field models in unitary gauge look like this action up here with this correspondence. So this L, if you're wondering what L actually is, well, in the context of single scalar field models, it is the potential, right? It's how the potential changes with time. If you're wondering what C times G, what C looks like, well, C is the kinetic degrees of freedom that arise in this context. We're in a situation where things are homogeneous. The gradient degrees of freedom don't enter into the analysis. So, okay, so this is to say that so this is a general action, right, which is describing a clock degree of freedom, a scalar clock degree of freedom, and a particular instantiation of this is single scalar field models of inflation. Okay, so in pictures, EFTs of inflation described in this way contain the simplest models of inflation as subsets, but it's agnostic, right, about the clock degree of freedom. So there's other possible models that are included here. So as I say, you can be completely agnostic about the composition of the clock, namely of the single scale, so this scalar degree of freedom, together with what governs the rate at which it ticks, namely something like the potential term. And so in the context of single scalar fields, you can remain agnostic about the composition of the inflaton field and the inflaton potential. And this model independence, I think, is important, right? It's the fact that you have a model independent way of thinking about inflation that allows you to tackle the initial conditions problem in a way that's different, right? You don't need to start with a specific potential. You start with a more general description of inflationary states. And then you can press on the initial conditions problem. So so I wanted to connect then this particular model of an EFT of inflation with the problems for inflation that I described earlier, the first thing to note is that, as I've said, EFTs inflation are model independent, and they really look to try and characterize what's common amongst these models that are responsible for the charge that inflation's, permissive, but there is a permissiveness problem in the first place. So they're not trying to break the degeneracy from that point, as it were, from that point of view directly. But I think this provides an opportunity, namely the opportunity is the following, that if you can generate a prediction from some EFT of inflation, I said this earlier, that's violated by observations, then you end up disconfirming each model in the class of models that is covered by that particular EFT of inflation. So in that way, right, EFTs of inflation could provide, break this degeneracy, so to speak, or disconfirm an entire class of models. But I don't think this is quite okay. This is a use of EFTs of inflation, but it's not the one that naturally jumps out at one. So in particular, I think the EFTs of inflation are better suited, naturally suited to addressing this initial conditions problem. And the reason, as I say, and as I said, is because of its model independence. The problem that arises and the limitation in the scope of this program is that one needs to worry about measures over initial conditions, and I think that problem remains. So we can certainly get into that if you're interested in talking about it. But there is a problem of measure. There's a measure problem that persists, I would say. Okay. So what I want to do next is to tell you about this particular model that we developed, provide you with some more details to show you how it is that we use this kind of framework to address the initial conditions problem. And so we took a particular EFT of inflation, in fact, the one that I just showed you, the one by Chung et al. And this follows by construction the time evolution of a background space of very high symmetry. It's homogeneous and isotropic and flat, and we extract the dynamical system from this particular EFT. So there are three parts to this construction and the ensuing analysis that I want to tell you about. One is you have to define these dynamical variables. The second is that you need to define the phase space that's given by the dynamical variables in essence. And then one requires a measure. And this measure will then tell you about the initial conditions that lead to sufficient amounts of inflation, where sufficient amounts of inflation are something like 60 folds of inflation. Okay, so here are the variables. So this is the original background action. And this work is built off of some work that was done by Frusciante and others in 2014, addressing similar kinds of concerns in the context of dark energy. So the particular variables that we have in mind are the following. So X, these are dimensionless variables, the sort of the expansion normalized variables. Each one of these terms gets a variable, so C and L, and then one requires an infinite tower, essentially, of other variables to fully describe the system. So you end up with an infinite set of dimensionless variables, X, Y, lambda naught, lambda one, and so on. And it turns out that you only really need to consider a finite number of these for a given phase space analysis, and I'll motivate this in a moment. But okay, so you can, these are dynamical variables. You can take the time derivative of these things, where time here is referred to is this log of the scale factor, and you can extract these dynamical equations fairly straightforwardly together with this one particular constraint. So this one constraint may look familiar if you stare at this long enough. You might recall that the first Friedmann equation looks something like h squared is 1/3 mass Planck squared C plus L. And so if you divide that particular equation by h squared, then you simply get this. X plus y equals 1 is the first Friedmann equation. So it's a constraint. This is the on-shell constraint for this dynamical system. And then you have an infinite tower of equations which describe the dynamics of the system. The particular quantity which will tell you whether inflation is occurring or not is this Hubble's slow roll parameter, as it's called, and if it's less than 1, then it's the case that inflation is occurring, and you can write it straightforwardly in terms of the dynamical variables that you've defined. So so this is an infinite tau, right? So this seems problematic. To extract a closed system of equations and to extract a finite dimensional phase space, and to in fact allow you to solve these equations, one way to do this, I think, the way we did it, is to set some lambda sub capital M to be a constant for some m greater than or equal to 0. So you set lambda sub 1 to be a constant, or lambda sub 2 to be a constant. If you do that, then this creates a finite dimensional phase space. Okay, so say you do it for lambda sub m, then you end up with a constrained system. This is the constraint of 2 plus m ordinary differential equations for the variables that are effectively dynamical, encode the dynamics of the system, the physical degrees of freedom of the system, x, y, lambda naught up to lambda n minus 1. And this is a closed system of equations which you can solve with the right kinds of initial conditions. Okay, so for this mth order system, I have the Hubble slow roll parameter is given in terms of this particular expression here. And using the constraint, you can write it purely in terms of this x variable. So one take-home message here, for the sake of what's about to happen, what I'm about to show you, is that inflation occurs if and only if x is less than a third. So you just need to monitor the value of x to know if in fact inflation is occurring. So then you can, so with this in mind, you can go ahead and, as I mentioned, analyze the framework order by order. So one order at a time. For the 0th order system, you fix lambda sub 0, and this gives you a phase space which is just 2-dimensional. So x and y are the effective dynamical variables here, and there is a constraint. So you have a 2-dimensional system which is reduced in dimensionality by 1 due to this constraint. You could then look at the 1st order system, and for that you'd fix lambda sub 1. This gives you a phase space which consists of little x, little y, and lambda naught. And these are dynamical equations, and they're constrained by exactly the same constraint, the Earnshaw-Friedman constraint, as it were, giving you a dynamical system which is effectively 2-dimensional. Okay, so just a little bit on how you interpret these variables before I show you some results. If you recall this comparison with the single-scale field models of inflation, I mentioned that C can be interpreted as the kinetic energy density, right? And L looks like the potential. So if that's the case, then this little x, which is C over really the total energy, is a density, is a fractional kinetic energy density. So x corresponds to kinetic degrees of freedom. Y corresponds to the fractional potential energy density, namely potential degrees of freedom. And these little lambda m's are telling you how the potential energy density is changing with time. So in particular, one thing to keep in mind is that when you fix lambda m to be a constant to give you a finite dimensional phase space, what you've in fact done is you've demanded, so you set by fiat, that the mth derivative of the potential scales with the scale factor in this particular way. So it's a result of this definition. Okay, so maybe we can take stock. I mean, I don't know if this is a good point at which to stop for a moment in case people have any questions, because there's a lot of formalism there. Feel free to jump in and maybe ask a question in case you want something clarified at this point. So maybe, so what you end up with once you've described the system in this way, and maybe to reiterate, right, we have this action that is an effective action. It is independent of the mechanism that gives rise to the clock. From this action, we derive dynamical variables. Dynamical variables are the kinetic degrees of freedom, the potential degrees of freedom, and a tower of variables which relate to derivatives of the potential degrees of freedom. translating this into single scalar field terms. But again, you don't need to do that. So, so you now also, as a result of this infinite tower, you end up with, in principle, an infinite set of phase spaces, right, of increasing dimensionality. So you can, I think, go through this, and you do go through this and analyze the physical system one phase space at a time, where there is a good reason, I think, to just focus on the simplest possible phase spaces here. And the reason is that higher order phase spaces, ones which are derived by setting lambda sub m to be a constant, are fixing something like a very high derivative in the potential term. You're fixing it to scale in a certain way with the scale factor, right? So if I fix lambda 1000 to be lambda sub 1000 to be a constant, then you're fixing the 1000th derivative of the potential energy density, right? And there's a good question as to why you might think you can do that. So, so we focus on the simplest phase spaces. The 0th order system here has 2 dynamical variables. It has a phase space dimension of 2. Again, there's 1 constraint, so it's effectively 1-dimensional. The 1st order system has effectively 2 degrees of freedom. There's 3 variables, the phase space dimensions 3, and there's one constraint, and so on. And so we looked at the 0th, 1st, and 2nd order term. So the 0th, 1st, and 2nd order system. So for each system, for every single system, every single phase space you see, there's 2 facts here. One is the constraint, and the other is that inflation occurs if and only if x is less than a third. And so the initial conditions that are relevant here are initial values of the x and the y variables. These are 1st order ordinary differential equations. And because x plus y is always 1, and x is something like a kinetic degree of freedom, and y is something like a potential degree of freedom, initial conditions don't expressly favor inflation, have the kinetic degrees of freedom higher, greater than the potential degrees of freedom. So we look at those systems which have an x value, initial x value. We particularly focus on those parts of the phase space which have an initial x value larger than the initial y value. So yeah, yeah.
This slide, so you're increasingly detailed. Am I allowed to be thinking of these as nestled subspaces, or like nestled hypersurfaces, I guess? Or
good.
Because that's what increasingly detailed makes me think I can think of.
No, so I was using, right, okay, good. So I think I was using detail here in the sense of there are more aspects. There are more derivatives of the potential like term that are allowed to vary. And so you're probing the potential like term with in more specific ways as you're going down. Yeah. So. All right, so here is an example of the 0th order system, right? X kinetic degrees of freedom, y potential degrees of freedom. X plus y equals 1 is this particular constraint surface. I have 2 fixed points in this dynamical system. Inflation is occurring anytime x is less than a third, and I begin with kinetic degrees of freedom that dominate potential degrees of freedom. So in this particular case, they're equal. X is equal to a half, and you flow towards this inflationary fixed point. Okay, so in this particular case, x is 0.9, and so the initial value of x is 0.9, so kinetic degrees of freedom are dominating, and you get this flow towards this inflationary fixed point. And it turns out this particular inflationary fixed point is an attractor. So if you were to start, I mean, if you were to even start over here, which is really potential dominated, you would also flow to this inflationary state, which is what you would expect. So in this particular case, initial conditions that aren't geared to trigger inflation, namely kinetic dominated terms, generally flow towards this inflationary attractor. And so there's no fine tuning in this particular context of sufficient amounts of inflation, 60 folds of inflation for the 0th order system, given this is a natural attractor. Okay, so the 1st order system is now 3-dimensional. You have, in principle, you have x, y, and you have lambda naught. You have inflationary fixed points, it turns out, This is a sort of different kind of inflationary fixed point to the one that you would have seen in the first order system. This has a sort of analog in the zeroth order system. This has an analog in the zeroth order system. But this particular surface is the constraint surface, right? This is where the Friedmann equation is satisfied. So again, you start with kinetic dominated terms, namely cases where x is greater than 1/2, as shown here, and then your three-dimensional spatial slice will flow to an inflationary attractor in this particular case. And this is in fact the scale factor of the universe as you're flowing along this particular trajectory. It's been evolved forward for, I think, 5 folds of inflation or something. But this is an attractor, so it'll in fact never stop inflating. Okay, this is a particular initial condition. For another kind of initial condition, you will also flow to this inflationary attractor. What's important about these kinds of initial conditions is that these conditions, not ones with lambda naught less than 0, it turns out they flow into regions which don't have single scalar field realizations. So you can take this kind of trajectory, and in the way in which I've described the evolution of the scale factor with time, you can map this onto something that you have a concrete handle on. You can map this onto a single scalar field realization. And in this particular case, you can't. So all of this stuff, all the phase space, so all the initial conditions that start below lambda naught less than 0, at least the ones that I've checked, which was a large fraction of them that are significant, don't have single scalar field realization. So this trajectory realizes inflation in a novel way, in a way that's inconsistent with the simplest models. And so again, initial conditions that aren't geared to trigger inflation flow into inflationary states. But we have new dynamics, right? Which is a possibility. It's a possibility when we had constructed this initial action, because we knew we had a sort of base, we had a clock in the background which was agnostic as to how it was realized, and you sort of see the benefits, I suppose, of the agnosticism come out in this context. Okay, so then to get a sense, I mean, the question of how have you actually addressed the problem in some sense arises, like how much of this phase space, how much of the real estate in fact flows to an inflationary state? How do you make probabilistic claims in this context? And the way we proceeded was to sort of a sanity check at some level. The probability claims are derived by postulating a probability distribution over initial conditions that are not expressly favored, and don't expressly favor inflation, namely kinetic dominated initial conditions. And then you compute the weight that's assigned to the initial conditions that lead to sufficient amounts of inflation. So, this purple region here corresponds to all the initial conditions that lead you to this inflationary attractor. So, so this is the basin of attraction of this attractor. This is a saddle point, it turns out. So this is an inflationary attractor, and all these initial conditions lead to this particular attractor. And the question is, how much of the phase space does this actually represent? And so to probe that question, I mean, there's many ways you could do this. To probe this question, we set down a Gaussian over this direction and just computed the amount of the initial conditions that lay under this Gaussian, essentially the weight that's assigned to these initial conditions as a result of setting down this Gaussian. So this is the sanity check, as I referred to it, that F is the width of the Gaussian when the width is very, very small. You're just really sampling these initial conditions right over here. All of these initial conditions are flowing right towards an inflationary state, so the probability is relatively high. As you spread this Gaussian out, you start to pick up these initial conditions here, which do not in fact flow into sufficient amounts of inflation, and so the probability drops. It always remains above 0.5 because you have this nice feature that all the initial conditions that lie below lambda naught equals 0 flow to an inflationary state, right? They push towards this attractor. So, okay. So some conclusions from this. So we find that sufficient amounts of inflation, so at least 60 folds, can be probable for the first 2 orders of our dynamical system. And so one can extract from this a claim about sufficient inflation being finely tuned or not. And for the first order system, we see an enhancement in the probability of flowing into inflationary states because when you include those kinds of trajectories that lie outside the usual single scale of field realization. So when you exploit the full freedom that's presented to you in this effective approach, inflation is favored. Okay, and so as I say, this includes dynamics that go beyond the simplest models, and because of that, there's I think this presents a more comprehensive way to tackle the initial conditions problem, and it does it in a model-independent way. Okay, so this is what I want to tell you about the work. Let me try and provide some context for what I've said, and to lay out what I think is the road ahead to try and use this kind of approach to make a more comprehensive statement about the initial conditions problem. I think what I've presented to you responds to a restricted version of the problem. We started, of course, in this homogeneous and isotropic state, and that's a big assumption. So there, as I say, remain a variety of issues that the EFT inflation framework needs to confront. And in particular, the spacetimes that EFTs of inflation probe are very special, and they make up a small subset of the possible cosmological spacetimes of interest, and so the worry is that they're not suitably general, right? And what does one mean by suitably general? Well, there are two ways to pass this. One is that one can make very strong assumptions about the initial state, and under such a condition, you're then just looking at something like the stability of the flow into inflation in light of perturbations, right? About this very strongly constrained initial state, which is strongly constrained to be homogeneous and isotropic. So much of the work has been carried out with regards to the initial conditions problem relates to this. Some of the numerical work pushes this a little further. Nonetheless, there's a weaker assumption that one could look to make about the initial state, which allows for very, very high degrees of inhomogeneity and anisotropy. And to really get at this question, I think it would be interesting to see an analog of recent numerical work, which invokes specific potentials that I described, but for effective field theory-based approaches. And also to develop analytical approaches that construct EFTs of inflation for backgrounds that are not just homogeneous and yeah.
So would this be separate? So still keeping x plus y equals 1 through inflation, or is that also being suggested to be relaxed?
Oh, I'm right. So I'm saying do this on shell. Okay. Do this on shell, but do it in such a way that you relax some of the assumptions that go into the equation, right? So you're going to pick up, let's see, you're going to pick up gradient lifetimes and things like this, but you're going to make sure that the basic answer equations are something like that. So I think that's useful analytical work, and this is work that I've been engaged in. I'm hoping in the next 6 months or so to have something else about this. And these are opportunities, I think, that exist in this context to try and address these foundational questions about inflation, but using this other way of thinking about inflation. So, okay. So let me just say, as a result of, set this aside, let me just say, as a result of this model independence, I think this is where the statement of it being more comprehensive comes from. And it's where one of its merits lie, this approach merits lie. The problem, I think the big problem, from a foundational point of view, is this issue of measure. So there is a measure problem here in cosmology. It's not the multiverse measure problem. This is a question about measures over initial conditions of a candidate universe that then flows into, for example, inflation. It does not flow into inflation. And it's a general problem. The probability distribution that I showed you earlier was obviously ad hoc. It was just designed to give you a sense of how much of the phase space flows into inflation in a way that's controlled. You can control aspects of the distribution. But there's a good question here about what these kinds of things actually mean, what these kinds of probability distributions actually mean. At the very least, I think there's some sort of a subjective interpretation that one can apply, and there's a story that needs to be told here about why it is that subjective measures of this kind should guide theory development in some way. And one would need to get that kind of project off the ground to really make sense of them. Nonetheless, I'm optimistic in this case that one can make such claims reasonable to some degree, if not provide justification for them. Okay, so the concluding thought is the following, that regarding this initial conditions problem for inflation, we don't need to wait for a more complete understanding of the very early universe. We can credibly, I think, aim to evaluate whether inflation is susceptible to the same problem that it claims to solve. It's not the only motivation for why you might think about inflation, but it's perhaps one of them. And I think the issues that are involved are a mix of interesting technical issues that I described and some of the conceptual issues that I described. Okay.
Thank you. Okay, so let's do some questions. Is it okay if I stop sharing for a sec? And I'm going to put the whole audience up here. And let's see. I don't see you. Oh yeah, right, there we are. Okay. So I will put you there. I think the easiest thing is going to be for you to field questions and call on people. If people want to just like raise either virtual or real hands. And Feraz, I think given the way you're doing it, why don't you go ahead? He can unmute himself.
Oh yeah, go ahead, Christian.
All right, thanks. Thank you very much. That was very interesting. I didn't understand all the technical details. I'll have to study this in more, more carefully. But I think I understand the main idea, and I see how that would address indeed the initial conditions problem. My question is about the other problem that you called the permissiveness problem.
Right.
This was maybe not the central concern of you today, but at some point, maybe I didn't fully understand this, but or I got this wrong, but it sounded as if you thought that this EFT approach would take care of the permissiveness problem as well. And I don't see how that would work, I guess, because if I understood it correctly, what you do is in fact, you have a more, in some sense, more general characterization of a bigger class of models. So at the level of the very general characterization, of course, you don't have an underdetermination yet, but there's definitely a sense in which the class is much bigger than it was before, at least compared to the single scalar field models. And if you're worried about the specifics of the physics, of the physical mechanism, then isn't there in a way a worse underdetermination problem?
Right. So actually, you're exactly right that you are including a broader class of possibilities, and so you're not in fact distinguishing between them in general terms. The only sense, and it's more, I don't know, it's more of a logical point than anything else, in which I think it could make things easier, is that it can disconfirm the entire, if you get a generic prediction, right? Yeah, that is disconfirmed, you've disconfirmed the entire class. And what this tells you is that actually what you should do is not write down single clock models of inflation, but maybe multiple clock models of inflation, right? So maybe you move on to something like effective field theories of multiple degrees of freedom. And right, again, you're right, the same issue that you raise, right, exists. It's not going to be a way to necessarily pick out in general terms, right, one physical realization over another. But yeah, you're able to make, because you're able to, there's one sense in which that, because you can make general statements, you're able make a general statement, right? But you can disconfirm the entire class, but it's very particular in this sense. So yeah.
All right. Yeah. Thank you very much. That's very helpful. I do see that maybe if I may continue to ask a sort of a second part of that question about the initials condition problem. I see that the strategy is the overall strategy that you're pursuing is very promising, but I do worry about the measure problem. I think without really having a convincing answer to the measure problem, it's difficult to really claim to have solved the initials conditions problem then. Would you agree with that?
Right, so there's a question here of the kind of solution that you'd be willing to accept as being a solution. And I agree that, you know, if there's no agreed upon justification for the measure, then there's going to be no agreed upon answer to the question of whether you've solved the measure problem. And the kind of optimism that I was expressing is really an optimism about the way in which we in physics typically use sometimes heuristic measures to make claims about theories, right? I mean, the initial claim about inflation solving something like the flatness problem, nobody, as far as I know, set down a specific probability distribution that everybody agreed upon. It was more the case that, look, we saw that there was this sort of universality that arose in the context of inflation. This universality can be cashed out in terms of something like uniform distribution, but you don't have to. There is a, you know, this sort of a stability / universality argument that one could make. And that's the kind of reasoning that led to, you know, okay, it's one aspect of the reasoning that led to inflationary cosmology. And I think that that's the kind of reasoning that you would need to buy to really think that the solution that the program that I'm laying out could provide a reasonable response to the initial conditions problem.
Okay, great, thanks. That's very helpful. Thanks a lot.
Yeah.
One or two. I guess the first one I'll ask because it's sort of anti-symmetric with the previous one.
Okay.
So I'm so dramatically not a particle theorist that I have no qualms whatsoever shifting to the more general class because I'm not cashing out physics in terms of each different potential model being a different particle model or something.
Okay.
So
you're happy with the generality?
Right.
Okay.
Yeah, things that are lost are sort of superfluous to the cosmological physics. So I think that means I see no cost to moving to the generality.
Yes.
The flip side is, what else do I lose by not being interested in particle physics? And I think it's my comfort with the on-shell constraint.
Yes.
And here's why. So maybe this question is confused and you can catch me where there's something going wrong, or maybe it's something more fundamental. Originally, so 1981 inflation, it was fine to help myself to the background standard model, you know, Robertson-Walker structure, general relativity, and I'm talking about one further particle on top of the inflaton. If I'm throwing away this idea that what we're doing in structure formation or early universe cosmology, if I'm throwing away the idea that we're trying to find that one missing ingredient that can do some interesting work, and instead just treating it as I want a robust early universe theory of structure formation or pre-structure formation or something. Don't I simultaneously sort of lose the ability to rely on the nice uniform background that was all of the other ingredients besides that one further particle? Does that, yeah, as I say, it might be a confused question in itself, but.
So you had your original question this on-shell constraint being something that you're, I mean, let's see, there's two ways to, I may not be addressing this issue, but I would always include the on-shell constraint. But the on-shell constraint is not just on-shell with regards to a homogeneous background. It's on-shell with regards to whatever dynamics you introduce, whatever extra fields you introduce.
Well, so maybe I'm confused on technical point as part of the question.
Right.
So the extent to which you had the qualifier at the end that the existing work thus far is really only tracking light perturbations.
Yes.
On the background.
Oh, yes.
Part of the grounds for that, I was thinking, were that this constraint, in addition to making sure we're still in general relativistic sort of space-time, on top of that, at each moment in cosmic time, we have a nice uniform zeroth order structure.
I see. Okay, good. Okay, good. So I think the claim that I'm making is right. Is that the actual EFT? So this EFT is some sort of expansion, a perturbation expansion about a background. And my claim is not that. Is that the kind of EFT that I'd be looking to develop is one that's sort of intrinsically anisotropic, for example, right? Intrinsically anisotropic or somehow intrinsically homogeneous. That's not necessarily a perturbation. That kind of EFT is the kind of EFT that I would need to get off the ground to address the kind of problem that I have in mind. And there I would assert something like on shell for that case, right?
I see.
Yeah. Oh, sorry. Yeah, and the only other thought that I had was maybe, and I thought this is another part of the issue that, and this may not be part of the issue, but the kind of dynamical systems that one ends up considering in this case are, right, there's a constraint, but if you pick up the right kinds of fixed points, those constraints, the conclusions that you draw about the dynamics can be insensitive to some degree to being off shell. Right. So in the sense that if you choose like hyperbolic fixed points, for example, these are fixed points which don't change in terms of the sort of qualitative phase space character under changes of the equations of motion themselves, small changes of the equations of motion themselves. So that's a useful thing to keep in mind. Not a necessary thing to keep in mind, but a useful thing to keep in mind.
So I guess a related question. Yeah. Presumably there's nothing stopping us from doing an EFT approach as you were describing for the rest of the universe, for standard model cosmology.
Oh,
right. Or is there? I mean,
so when you say standard modern cosmology, you mean now you mean dark energy? What do you mean?
So yeah, I mean dark energy, but I also just mean the dust, which isn't particularly fundamental.
Yes.
But presumably I could set up everything. I wouldn't get the nice dictionary translation between my particular favorite fundamental model because there isn't one, it's dust. But the general structure would still go through, and I could think about the entire sort of large scale degrees of freedom history of the cosmos.
Yes.
Effective field theory.
Yes, absolutely. EFTs all the way down or up.
Sure.
Yeah, exactly. Right, and sort of piecing them together in such a way as to flow from one EFT to another. Yeah, I mean, so there's a sense in which here, what I've described is just an EFT for a very specific energy scale, right? And the kinds of degrees of freedom, so this may be, but I think it relates to an aspect of what you're saying, that I was talking about flows into inflationary states, and these are dynamical attractors, right, which inflate forever. So this is clearly not a realistic setup. This is kind of a setup to get you into a particular inflationary state, and then the question is how you get out of it, right? And
leave the never-ending fixed point of inflation and get to a different?
It's a tricky issue. Yeah, because one ends up with sort of issues with reheating that are where the physics is uncertain. I haven't seen work that addresses that in an EFT point of view. I may not. If you do know of something, I'd be curious to hear. Yeah, but I haven't seen that. Yeah.
So this was sort of following on, I mean, or related to what Mark was asking, but actually for this nuanced question. Could you explain the sense in which these are EFTs? I mean,
oh yeah.
I mean, is it sort of in the sort of Wilsonian kind of sense that, you know, with the degrees of freedom integrated out? Is that literal, or is it a little more kind of metaphorical here or something?
So it relates to so these are bottom-up effective field theories. So they aren't. It's not the case that you've taken some sort of theory, integrated out degrees of freedom, and landed in this space. This is the hope is that by writing down an action which obeys certain rules, right, which is general in some sense, obeys the symmetries of the background or symmetries you think are relevant at the scale, that you will capture the different degrees of freedom you could excite were you to have started up in some sort of top-down calculation to kind of integrate out degrees of freedom. Yeah, but so it's bottom-up from this point of view.
Okay.
Yeah.
Good. No, that's
Right.
That's helpful.
Yeah. Yeah. I don't know of examples of top-down cases in the context of inflation.
Right. But I kind of understand sort of conceptually. But when you're talking about the tower of EFTs,
Oh yes.
Mike, imagining if you went to a higher energy scale.
I was going to lower energy scales in this particular case, but yeah, in getting you out. Yeah.
But I will say, I mean, part of the spirit of my asking this question was it might be very nice in getting a grip on how higher energy physics would constrain the measure at the onset if we had a neat case of how inflation in a totally EFT, tower of EFT's universe prepares for the lower energy afterwards.
I see. Sorry, to your point, the measure, like the measure, the probability measure.
Right.
Yeah. Okay.
How a high energy theory could force our hands into a particular measure.
Yeah.
Like
that would be great. I agree. So that's right. So there's a very crude sense in which and it's in the spirit of the fact it's the bottom-up approach.
Could you explain that idea a bit more?
Oh, well, do you want to? Okay, let me tell you what I interpreted here is that it might be the case that something like our expectations about higher energy theories will tell us about our expectations of the various parameters that could arise and the probabilities which they might arise in the lower energy theory. Is that an accurate?
Yes.
Okay. So the only thing I was going to add to that, I think it's a great idea. The only thing I was going to add to this was that there's a crude sense in which the kinds of things that I was doing here in constraining the phase space in various ways was constrained by some sort of expectation of what a higher energy theory could possibly tell me, but not ever making that very explicit, right? There's a crude sense in which we can constrain parameters because we can say that, well, we know that this theory is not going to hold for super Planckian values or something, right? And so we set down bounds based on our expectations of when we think higher energy theories will kick in. So that's a crude sense in which this kind of measure issue is already in play here, but it's not as specific as the kind of solution that I think or kind of solution that you're suggesting. Yeah. Which I think is
right. So this is something like the analysis you presented and the more flexible versions of it that you're currently working on,
right,
are they're focused entirely on initial conditions on onset of a particular energy scale inflation. Meanwhile, implicit in the framework itself is that we're having to assume that certain things can't go wrong after that onset.
That's true in the sense that you're following the formalism once you set the formalism down.
Sure.
Yes, yes. I thought you were going to say that there's this assumption that somehow the higher energy physics isn't going to spoil in some profound way the statements that you're making about the onset of inflation.
Ah, good, right.
Which is a
I
worry.
might have said that too. Yeah.
Okay, which is a worry.
Right.
Yeah.
I see.
Sure, that's a worry.
Sure. Yeah.
Yeah.
Okay, and then this would be a situation where forgetting about even higher energy physics,
Right.
if we're just asking something like, why doesn't inflationary scale or GUT scale, if that's a thing, why doesn't that scale physics spoil the onset of the lower energy sort of linearly expanding universe? And that's the kind of thing where we do have a good, one would hope we have a good answer, and it would be a story about reheating.
Yes.
Which is that something about the way those two levels of the tower are stitched together means we can safely assert that gut scale physics is no longer relevant.
Yeah, that's a good point. So this goes right. This goes through inflation to the next sort of energy scale. Yeah, the worry. That's right. So this is focused, and in fact, even the generalized things that I'm thinking about are really focused on really just the sort of energy scale of inflation. Yeah.
So
Okay.
I don't see any more hands. If any hands there. So I have a more elementary question that sort of struck me when you put up the drawings about the inflation attractors.
Right.
And then you said some things that kind of were starting to address what I was wondering there. So could you explain how that kind of works exactly? So does the system actually have to reach that fixed point? Does it actually reach that fixed point, or is it enough that it gets close to that fixed point? How should I interpret those drawings a little bit more?
Yeah,
that
great.
would be kind of helpful.
No, great. So I think that the interpretation that we have in mind is that, well, I think the natural interpretation is that this is a system that's to be trusted for a certain amount of time, right? So another way to think about this is that if you look at the single scalar field realizations, the trajectories which are consonant with a single scalar field, then you're not going to trust things like super Planckian excursions of your scalar field phi. And so, so there's a sense in which, right, you're going to trust this theory to some extent. This is really meant to try and get you into inflationary states. And right, so I was evolving things for 5 e-folds. You can do it for 60 e-folds. They'll go on forever. Right. So the interpretation, I think, really is a very I don't use the word honest, but it's restricted. The effective aspect of this is looms large. That it's really a claim about getting you into inflationary states, and then you need to worry about how to get out of them. But that's not quite addressed by this. Yeah.
But in those drawings, what does it mean to get into an inflationary state? Do I have to actually run right into the green dot, or is it enough to kind of get close to the green dot?
So in this case, it's enough to get close to the green dot. And as long as you get close, so you can track how much inflation has happened as you get close to the green dot. And as long as how much inflation has happened is sufficient, where sufficient is 60 e-folds, roughly, then you're done. That's the point.
All right, so I should sort of imagine a kind of dotted circle around the sphere around the green dot, and I'm trying to get into there.
Right. Or maybe just a sort of a time scale, or a sort of a time window of interest. Right. And the time window of interest is the idea is, you have these conditions that hold at the time when you think the EFT applies, and then let's see what part of that real estate what part of those conditions lead you into sufficient amounts of inflation and stop the analysis at that point.
Right. I mean, I guess beyond that, you don't kind of trust the analysis.
You don't trust
in any
it.
case.
Exactly, right. So there is a sense in which it really does, this holds for around the Hubble scale, right? The EFT framework to begin with applies at Hubble scale. And so we trust it, we follow it.
Right.
For that kind of
Okay. Okay, so that's good. So what's good? Right. So I mean, the strength of the result is to show I don't really have to kind of build in initial parameters to get this behavior going.
That's right.
But I still do have to have the right kind. I mean,
Yes.
there has to be something that's driving the inflation here, right? Built into the.
That's right.
Into the potential is still just an inflation potential or something.
There's
that's assumed in there,
right.
Right.
What you're assuming is that there is something breaking the symmetry, the basic symmetries of the underlying spacetime, right? That's where I think this assumption.
The clock field.
The clock field. Yeah, the clock field. Right. The clock field is what's breaking the symmetry. Inflation has to end, so that you don't have this sort of plain translation invariance anymore in the background. That's where I think the scalar degree of freedom enters into the analysis. And then, that scalar degree of freedom doesn't necessarily have to lead you into inflation. It can lead you into all sorts of different kinds of behavior. For the scale factor, some of them lead you into inflation, and some significant amount of leads you into inflation.
Right. So just to say that again,
yeah.
I thought I had it, and then said something at the end that made me worry that I didn't.
Okay.
But sort of the result is within this framework, kind of as soon as I have this clock field, and now thinking about your graph of the probability, the sort of probabilities,
yes.
It actually becomes a lot more likely that it's always going to be above 50% that I end up with inflation.
That's certainly the result, but I don't know if it's I don't know if that's to be expected.
No. That's kind of what the result is.
Oh, yes, that's right.
Kind of surprising.
Right.
Yeah, no.
Okay, sorry, yeah.
No, but that's how I should have. That's my kind of whatever slogan kind of takeaway from this. Okay.
Yeah, right. That's right. Another way to frame this is that when you allow for there's a greater flexibility, it's not necessarily the case that greater flexibility spoils inflation. It in fact enhances inflation. Where the greater flexibility is cashed out in terms of a clock, which is not specified beyond the fact that it's something that breaks time translation in the back.
Okay. So I've got my clock. You then write down the particular action that involves the clock, and so the action is something like the difference of the potential and kinetic energy. Is that also forced on you just by the fact does the action have to have that? I mean, just that I say I have a scale of have a clock field that's just whatever takes on constant values of my constant.
Right.
Increases. It's increasing. Is that the only form the action can take for such a field?
So the general form that the action can take is anything with this clock field that's breaking the background, anything that's composed out of the degrees of freedom that you're left with in the system. And the degrees of freedom that you're left with in this 3+1 decomposition, metric degrees of freedom, extrinsic curvature tensor, Riemann tensor.
Actually, I meant the clock part of the action. Does it have to be that form?
Oh, what I was going to say was that
I write down a different sort of.
Yeah, so this is a specific expansion. And different expansions will give you, in general, different forms, I believe. I haven't computed them myself, but you can. This is an expansion about an FLRW background with small perturbations about that. If you break some of the symmetries there of the background, so say you are really interested in something like an isotropic background, you pick up other terms. You pick up other terms.
Okay.
So the G00 that you saw there you'll see other kinds of terms.
Because otherwise, the symmetries of the background mean that's really the only action, the only action I can have for the plot.
In this particular context, yes. When I'm expanding around a background space.
Yes.
Yeah, exactly. Yeah.
Okay. Oh, so that is pretty strong then. That is, yeah. Okay.
Yeah, right. I think that's the strength of using this particular way of thinking about inflation for this particular problem.
Yeah.
This characterizes the strength.
Okay. That's good.
So to connect a dot to a different, so if you wanted to start doing the same approach on, I'm forgetting which level, but whichever the Bianchi
Yes.
class that
Good.
you track a scale factor in two different directions.
Yeah, the Bianchi one is in 3 different directions. Yeah.
Okay.
So and then I guess yeah, if one of them's okay, yeah.
Bianchi one is
Every
spatial
direction is a different.
So that would be a 3 clock inflationary EFT. Is that? Am I allowed to make that leap, or is that?
Okay, so how's the best way to think about this? Right. So the question is, what do you mean by inflation in that context? Because now you have 3 different degrees of freedom. So if you describe inflation as sort of an averaged kind of expansion, then you really have a single clock in the background. And that's how we're this is how I'm developing this kind of approach. That you have a single clock in the background that's sort of driving the. Now, I don't know how to think about it with extra clocks. That's interesting.
I've always been somewhat confused about multi-clock proposals.
Oh, yeah.
I was wondering whether there was a cheap and easy way of understanding
Let's
this.
see your points. I kind of think about this.
Well, we should probably wrap things up. It's 1 o'clock, and we can talk about it some more on the lunch. Get some food in before we do. Okay, so thanks so much for this great talk and this really nice discussion. I think there's a bunch of people saying goodbye in the chat as well.